Uh, so I think I would prefer to just as it was essentially yesterday, not to talk about myself about any generalities, but first of all, see if people have questions uh, to today's speakers. So let's see. Yeah.
No, I have a question for the.
No, this is to be idea that you come here.
It's supposed to come there?
Yeah.
I have to scream.
No, the idea is, you can put this thing on the screen.
Well, so the question is whether these classification theorems of the superalgebras and so on that you showed us, they're reminiscent in some way of classification of finite simple groups. Of course, there's the connection by moonshine between vertex operator algebras and the monster and so on. Have you thought about this? Can one make any link between between say sporadic and the families of simple groups and this classification? I mean, it's a pity not to have all the mathematics come together in the last few months of the millennium.
You're so close. Yeah. No, you see, the monster is really the group of symmetries of a single vertex algebra. You cannot say that vertex algebras correspond to simple groups. And there is no connection to sporadic groups of this class.
V8 is connected, for instance, with the Leech lattice in some way, and the monster. There are connections. Or not?
Not really. It is just similar. The root lattice of 8 is similar to the Leech lattice. There are some parallelism, but no. And what is in what way there is any relation to finite simple groups of this stuff? I don't see. So we have to wait for the next.
It's worth a try.
Okay. Any more questions on any?
Ask questions. There was a picture by. Here we go.
No, it's just continuation of the previous question. There was a conjectural picture of Vogel of unifying all simple Lie algebra, finite dimensional Lie algebra, superalgebra, and so on. But did you try to think about infinite dimensional things? Also, maybe one family, few incarnations.
Actually, Maxim already asked me this question. But I never got around to study the work of Vogel, so I can't say. Yes, of course. But is he here? Yeah. Maybe you can give some more explanation about this Matibik homology. What is the definition of something?
Put this thing on.
Well, there is a number. There is a bunch of definitions. They're all equivalent. They're all look rather unpleasant. So the simplest one, if I only want to work with smooth algebraic varieties, smooth quasi-projective algebraic varieties. If X is a smooth quasi-projective, then the simplest thing I know is to consider a complex whose nth term consists of cycles on the product of X and a, let's say P, which are delta n. which are equidimensional on this X cross delta n. And delta n is, again, so subspace in here given by the equation sum of the coordinates equals to 1. So it's an algebraic analog of a simplex. Except in simplex you also put some inequalities, but here it just ignores these things which go to.
You wrote just a hyperplane.
Yeah, that's what it is. That's what delta n is. It's a hyperplane given by the equation sum of the coordinates equals to 1. And then I take x cross this delta n, and I take cycles on the product of this thing with another affine space, which are equidimensional of relative dimension 0 over this product. So there are no jumps. There are no fibers of non-trivial dimension. And this thing forms a complex because there are maps between the simplices just as between the usual simplices. And so restricting cycles to this sub-simplices, one gets, this becomes a simplicial abelian group. So taking these restrictions and then alternated sum, one gets a complex. And this complex computes, in the case of smooth quasi-projective varieties, its Mativik cohomology. And two indices come from here and here. These are the two. Huh? Well, no, it's actually, this term will compute H. Let me think 1 second. 2p minus np.
After some computers, there's all cycles with this operator.
Well, because it's no, this is just cycles, honest to God cycles. But since it's a complex, then the equivalence appears when you take the cohomology of this complex. For example, if one takes C, so C0 just consists of 0 cycles on X cross. This consists of cycles on X cross AP, which are equidimensional over X. This equidimensionality is at this point irrelevant. It's easy to show that any cycle can be deformed to such one. So this basically, C0 is sort of all cycles on X of codimension P. And then C1 gives the families of such cycles parameterized by the affine line. And so the quotient of C0 with respect to C1 becomes exactly the Chow group of cycles of codimension P. So this is the case n equals 0 here. And of course, it's closely related to Spencer's definition. So this complex computes cohomology because it's strictly contravariantly functorial with respect to all maps in X. Any morphism from Y to X gives a map of complexes. If I modify somewhat the condition on cycles, then I'll get the Spencer's complex, which is bigger, which computes Barrel-Moore homology and has somewhat different functoriality, but which is quasi-isomorphic to this one. And this is definition of Mativik cohomology.
So it's not much harder than singular homology.
No.
One of the things.
No, it's not much harder. Well, the vanishing conjecture says that, for example, this group is 0 for first index is less than 0. So it means that n is greater than 2p. So how to show that this complex becomes exact when n is really, really great, really big, is completely unclear.
It has some meaning, this conjecture, naive geometric. Feeling behind it or what?
Naive geometric, well, the only meaning it really had originally, I suspect, is that the only way to detect elements in these groups is to construct a map from this group to something actually computable. And all the things actually computable turn out to be 0 if the first index is less than 0. So there was no series to detect elements. In all known series, there is 0 because the corresponding groups are completely 0 by definition. So it was conjectured that in fact, they're 0 also. It is really that bad. I mean,
These are dualities of cohomology, you can say co-cycle, pair, or usually how you detect something on 0, like cycle, co-cycle.
no, here this is kind of things don't require any vanishing in this part. They all, I mean, the duality compares homology with cohomology, and then it becomes vanishing turns into a statement about homological dimension, which is maybe it's more reasonable, but it's no less hard. That's it. If there's something else while I'm staying here.
Are there approaches to any at least ideas how to approach
Vanishing.
vanishing?
Not really. Well, this was the only thing what I was trying to say at the end of the talk. Now, bad thing about vanishing, so one should speak about vanishing for different weights, different values of p. So it's trivial for p equals 0. It's very simple for p equals 1. And it's completely impassable for p equals 2. So there is this huge break. The last doable case is very simple. There is no hard doable particular case. And somehow one wants to create such a thing. And the only thing which comes to my mind is if I can represent motivic cohomology, I say it's the same as this homotopy group, so stable homotopy groups, then I get additional filtration. I get representation, well, let's do it this way. So if this is true rationally, this gives me a description of this group as a colimit of phi I plus n j plus n, say, s and n. It's better get something like this. So I get a representation as this long colimit. And if I want to prove that this is conjecturally, this is 0 tensor Q for what it should be, I greater than 0. Then I can look at the separate groups, not at this limit, to the separate groups. And each of these groups, it should, but we don't quite understand it, have a geometrical description. It's more or less, well, elements in these groups are represented by rational maps from one projective space to another. So this passage from cohomology to stable homotopy groups is, in a way, has a lot to do with linearization. It's like if cohomology are represented by all cycles, then homotopy groups are sort of represented by linear cycles. This is not a precise statement. And then one can try to analyze the stable, find what is the first one.
Do you expect them to be 0 for fixed n and m, or
No.
Die because it's...
No, it's in fact a little bit trickier. So these stable groups are not 0 in the range where the homology is 0. However, one can make a conjecture, and which is, say something like that any element in the stable homotopy group. So The analog of vanishing would be this is 0 for I greater than 0. This is, of course, this is not true. I mean stable, even not true. However, what does seem possible is that if I have an element here, then it's a product of something with an element E, which comes from pi pq, with q greater than 0. Any element with q greater than 0 maps to 0 in cohomology because of the certain property of cohomology. So there is, instead of pure vanishing, one should talk about some property of this composition, of this multiplication product. That all the groups of negative first index, the ideal of groups with the negative first index is generated by the ideal of groups with the negative second index, something like this. And there is one geometrical observation here, which is why I think it may lead somewhere. So there's the only groups which we can unstable, which we can really approach, are the homotopy groups of P1. This is the first non-trivial sphere, sort of. And it's easy to show that if I take pi and 0 of P1, then, and consider its map to Matveev cohomology, it will go to 2 minus n1. Then this map is 0 for n greater than 1. And the reason for it is because over pi 1 I have the Hopf vibration. And I can write the long exact sequence of homotopy groups. And I'll see that pi n 0, here goes pi n minus 1, 0 of gm. This is easily computable because gm is completely discrete from the point of view of this thing. And this is 0 for all n greater than 1. So any element in here lifts to an element in the homotopy group of this thing. And this thing is a sphere of the next weight. So it's necessarily comes from a smaller second index. So one would hope that there are some analogs of this vibration for higher weights, which can be used to prove vanishing. So that if one is able to formulate everything, do the technicalities, then it should become a problem of constructing some geometrical objects.
Any other questions? If you can explain how your computations of Epsilon are related to Lamont's computation of the finest thing, in terms of technique, is the technique anyway similar or not? So, but if you could,
Just briefly,
Put on this.
everybody's tired. There was a formula that went by rather rapidly at the end that I just write down again. You have a connection on a vector bundle, and you know that you can write this connection in terms of a connection. If you choose a trivialization, then you can write this connection in terms of a connection matrix, A. And in the case of a curve, you can write the connection matrix something like this. G dz locally around a singular point plus eta over z to the n. where eta involves, so these are forms from the base. So the relative connection is essentially this piece. Then the determining the conjectural formula involves the residue of the trace of dg G inverse times A. And the point is that this is the correction factor. This is what makes the Riemann-Roch, what modifies the Riemann-Roch that we know to be wrong, the one that would work if there were no singularities. And this, of course, by its very description, is local around the singular points. So the Lamont theorem is essentially that the global epsilon factor is a product of local terms. And so these then purport, in a special case, I don't claim this formula works always, it turns out the interesting values of n are n greater than or equal to m minus 1. And if n, this formula should only make sense if n is equal to m minus 1, and if g is invertible. So in a special case, this formula purports to give a formula in the geometric case for the local factors. There is no formula for the local factors in Lamont. I mean,
in Lamont's case, you have to choose an additive character or something.
yes.
Decomposition.
Yes. Well, I mean, in a sense, we've dodged that because we're working in the geometric case. The additive character gets replaced by simply the exponential. So to speak, God chose one for us. That's okay. I could make one comment about the motivic cohomology. Just amusing fact. If you take the more naive definition, it just involves cycles on affine n space. So you have cycles on affine n space, and I won't go through it, but it turns out that the conjecture, the vanishing conjecture, is essentially equivalent to the statement that there are no interesting cycles of codimension less than 1/3 the dimension here. Okay, and this is a theme that's come up again and again for algebraic subvarieties of affine space or projective space, is there are no interesting ones of low codimension, and that's
how you complete the section conjecture, right?
yeah, something something like this. For example, there are no interesting two-dimensional cycles in 4 space. No, sorry, one-dimensional cycles in 4 space. There are no there are no interesting. I'm sorry, it's late in the day, but it says it's 1/3. The codimension 1/3 is kind of the. Sorry.
Conjecture is local dimension, right?
I've got it. Codimension. Yeah. It says.
Local dimensional cycle.
Yeah. Yeah, I mean, it's too late in the day to sort it out, but it basically translates into the Hartshorne conjecture for algebraic cycles.
But, does it really translate? I mean,
No.
we really have a theorem that one is equivalent to another.
No, it's just, I mean, this, after 6 o'clock.
So this might be one of the directions of
Yeah, I guess I wouldn't really recommend it. I mean, I think you'd have to smoke something extremely strong before you try that approach. But it is amusing. It is amusing that the same number, the same 1/3, comes up. Yeah.
Okay, any other questions? I think we'll